Okay, good afternoon. I'm Harry Atwater. I serve as Division Chair for the Engineering and Applied Science Division at Caltech, and I want to welcome you to the 2023 edition of the Wouk Lecture. Wouk, W-O-U-K, not woke, so we're very honored to have today with us Professor Chen from MIT, who's going to challenge us to rethink the subject of evaporation. And so that's, I think, we'll in for a very interesting and thought-provoking experience there. Professor Chen is the Soderberg Professor of Power Engineering at MIT in the Mechanical Engineering Department. He served between 2013 and 2018 as the Department Chair for Mechanical Engineering. He's been a longtime faculty member, and I think it's fair to say responsible for much of the hiring and startup of faculty who led to a resurgence and a very broad diversification of the department at MIT in terms of its disciplinary focus. Previously, he has also been a faculty member at Duke and at UCLA. I think the first time I met Gong was when he was at UCLA, right across town. He was a graduate of the Mechanical Engineering Department at University of California, Berkeley, working with Chancellor Chen, and is the recipient of many awards. I'll just note a couple of them. The ASME Frank Kreith Award in Energy, a World Technology Award in Energy, and the Erlangen Medal from the Society of Engineering Science. He's world-renowned for his work on thermal energy and thermal transport, and very much a research leader in this area. As I mentioned, he's been recognized with many different awards. I'll just note that he's a fellow of a number of societies, including the American Physical Society, the American Society of Mechanical Engineers, and is a fellow of the American Academy of Arts and Sciences and a member of the National Academy of Engineering. So Professor Chen has had a prolific and creative research career. He's been an outstanding mentor to many students, including our own Austin Minnick here at Caltech, and has had many research accomplishments that have been noted and recognized. And I think it's also fair to say that Professor Chen has experienced the most exhilarating but also some of the most agonizing aspects of being a scientist in the United States. And the thing I'm referring to is the fact that despite his career and a long tenure as a US citizen, naturalized from China, in January of 2021, he was arrested by the FBI in a dramatic case and charged with concealing his associations with and research collaborations with research groups and centers in China. In reality, what he was doing was, on behalf of MIT, building international research collaborations of the kind that we very substantially benefit from all of our international collaboration. And during a period of approximately 1 year, he had he was under a virtual house arrest and was forced to do his science pretty much by himself. So has had I think also an experience that serves as I'll say a notable and a bellwether of our times, this both working to achieve scientific achievements and also in a situation of growing tension and adversity between two great countries, the United States and China. He was, of course, exonerated of all charges in this regard, and I'll note was steadfastly defended and supported by the MIT administration in this regard. So we're delighted, and I think it's also fair to say that this provoked him to think about new directions in science that we're going to hear about today. So I'm really excited to hear about his thinking about rethinking evaporation. So, Professor Chen.
Thank you. And thank you, Harry, for that wonderful introduction. And let me just repeat that I've been saying, really from my heart. I'm a luckiest among unlucky people because I know a lot of people went through a lot of hard times, and they still going through this. And nowadays I do my science, and I also am a conduit for a lot of those people, and I talk to government and do my public surveys. I'm very grateful for Harry and the colleagues at the Caltech for inviting me back, and this is a great, for me, this is a great opportunity to show that I'm still doing my research, and in fact, particularly for graduate students today, I want to set example that we have to continue to learn new things. And what I talk, I can also say at the front, what I'm telling you today could be completely wrong. I'm still convincing people we're right. And, but I joke that, okay, the difference of me from you, most of you young people, is I'm a 10-year professor, so I won't be fired. MIT didn't fire me under the extreme case, and they won't fire me if I'm wrong, right? So scientifically. Really, as Harry said, but let me also say, Dr. Victor Wouk, of course, I didn't have the opportunity to meet him, but I'm very inspired by his story and the visionary in the hybrid technology. It's an extraordinary life. So, as Harry said, that during the 2021, I was pretty much, I couldn't talk to anybody. And in fact, the judge said I couldn't talk to any potential witness. I couldn't say I was able to move around in Massachusetts. I actually came to California, but I had to go for a committee meeting of National Academy of Engineering, and my lawyer had to go to the judge to actually apply for that meeting. So I was very fortunate to be able to come to California to attend that meeting. But that year also gave me a lot of time to think. This is a puzzle that started before what I experienced. So I'll tell you more like almost, it's not the best scientific way, but I'll tell you the chronological order because of the topic I'm going to talk, we haven't been able to publish anything. We couldn't convince people yet, right? And I will mostly talk about the optical evaporation. At the end, if I have time, I'll talk a little bit on thermal evaporation. But see, I think the optical evaporation is something that very radical. And thermal evaporation is basically saying since we all did it wrong, but the optical evaporation is something radical, and I could be completely wrong. So let me start with the thermal evaporation. We know is ubiquitous. We say that every morning when the fog is there, and we know this evaporation needs energy. And we know the latent heat, we know the sensible heat, and those are the numbers that we can easily use to calculate a thermodynamic limit. And one of this limit is under the sun, right? How much solar energy coming in and how much water you can evaporate. So that is, I'll give you the number later. So this is a starting point, right? We are all familiar with. And the next point I want to point out is that water does not absorb visible light, right? And if you look at the absorption depths at the green light, the peak of solar energy, the propagation depths could be 40 meters. In fact, once I was talking to the department, and the faculty working in the underwater communication said, oh, light can actually propagate 2 kilometers. So it's very weakly absorbing to the visible light. And that's why we see the clear water at the bottom. And so when we want to evaporate water, right? So the motivation for me to get into this is more in the desalination kind of application. And in fact, when we first get into this, it was Lamy Halas, and in fact, before Lamy Halas, Ravet pressure, and they were putting nanoparticle in water, and as a solar absorber. And Lamy Halas published a paper in 2013 and say, okay, around every nanoparticle, they're boiling, and the plasmonic effect. And Harry worked a lot on plasmonic, and we worked some on plasmonic, and that got that interest because it's a heat transfer, it's optics. So I started looking into this. We never had any funding. I had the postdocs that are working on much harder to publish a subject. I said, okay, maybe this could be a side project. So, but we looked into this. At the end, we think we reached a conclusion. It's really not an individual boiling around each nanoparticle. I think Lamy also reached a similar conclusion. It's really the bulk average water temperature rise. But with that as an inspiration, because their application in desalination and sterilization, it could be very cheap, we say, okay, we can do even simpler. Because if it's a thermal process, I just put something on water surface. I don't put a nanoparticle underwater. And it's a porous material, so it's a two-layer structure. So first we have an insulating layer, and then we have a light absorbing layer. It's porous. It's just a capillary force to draw water to the surface. Well, the black surface absorbs solar radiation, and you just evaporate water. So it's a very simple experiment. And when we say publish the paper, it drew a lot of attention. And you can calculate, like I said, you know how much solar energy come in. We know the latent heat and sensible heat. And the number, thermodynamic limit, let's suppose all the solar energy converted into heat, you get about 1.5 kilogram per meter square per hour, right? That you can consider that's a thermodynamic limit because I'm converting all the solar energy into the thermal energy of water, evaporate water. So we published a few papers, and a lot of people published more on different materials. And so one work that surprised us. This was the work of Professor Guihua Yu from UT Austin. And in 2018, they published a paper. They say they put a hydrogel, and this is a polyvinyl alcohol hydrogel, which doesn't absorb light. But then they put something black. They put a polypyrrole, and later on they put many things. And they reported the evaporation rate gets to 3. That is twice of the thermodynamic limit, right? I said under one sign you get a 1.5, and they say now they get 3. And let's don't talk about efficiency yet, because when you have 3, you're really super thermal, right? So how you calculate efficiency. And but that surprised us. And in fact, I got a colleague send me the paper. One of my former students was actually the co-author of this paper. And I said, this is impossible. So I just brushed it aside. This is 2018. I remember Guihua, they actually invited me to go to UT Austin, gave a talk. I think I was a department head, too busy. So I went there, I gave a talk, but I forgot to ask him the work. So, but see, they propose a mechanism. They say, okay, water is different inside the hydrogel. There are 3 kinds of water. The water-bonded polymer, they're water-free, bulk water, and they're intermediate water. So this is a picture that the people in hydrogel actually established before. But they say this has a reduced latent heat. And so at the beginning, I just don't believe. So like I said, I went there, I forgot to ask him, I forgot to look at his lab, I gave a talk, I came back. But then in 2019, this is where the international collaboration is really important, because I got a visitor, Jiawei Zhou was a PhD student at the time who was working on polymer hydrogel thermal conductivity, wet water. But then when Dr. Yao Dong too came under his own support, I said, no, we have money, he wants to work on this. I said, why don't you try to repeat Guihua's experiment? So, and I also had a chemist visiting, and she was a chemist, so we could make a material. So we're trying to repeat their experiment, and we couldn't. So I picked up the phone, I called Guihua, I said, can I send the people to you? So actually 3 of them went to Guihua's lab, spent a week there, and they came back. They couldn't repeat the experiment. But they brought a piece of sample, and then we put it on our solar simulator, and it worked. So that sort of convinced us that we need to continue to improve our material. We're able to eventually make the material and have a similar performance as what they reported. So we can get to twice of the thermal evaporation limit. So in fact, so in 2021, when my lab was pretty much gone, and the last, postdoc, Yao Dong was still there, I said, I got to get in the lab. I actually asked a special MIT General Counsel permission to get in the lab. That was later, that was the first time I went to lab, make our own sample, in probably another 15 years. So being a graduate student was not easy. And I couldn't make sample work. At least I was trying to learn the process of recording every detail, but I learned it was not easy to make the sample, okay. And so what's the mechanism? Because I basically repeat the Guihua's experiment, and so because I worked in optics, I said, well, I don't quite believe in his explanation, and maybe it's some photon effect. I don't know what photon effect. I said, rather than doing solar simulator, let's get a LED. And let's do wavelength-dependent evaporation, right? You don't expect this because when you measure absorption, this is the absorptance. It's flat as a function of wavelength. But when you measure evaporation rate under different LED, you see a peak at 550. Right? Around, say, here, the green light, it has the highest evaporation rate, which is puzzling. It's because the green light water is least absorbing. But of course, in this sample, there's a polypyrrole but this is already twice of the thermal limit, right? So I was very happy. This is a photon effect. And there's another piece of evidence. So we measure the vapor phase temperature. So measuring the vapor phase temperature was not easy because when you put a thermocouple on the light, it heats up. So we have to be very careful. And in this case, we do shielding, we shape our thermocouple. And this is comparing the blue. The blue is a thermal evaporation. You just heat up thermally. And the purple here, the orange here is the under light. And you can see there's a flat temperature region. And in fact, the temperature decreasing rate near the surface is faster under light, and then there's a flat temperature region, right? This is another puzzle. And again, it's very exciting to say this is a photon effect. But we still try to say, what's the photon effect? What kind of, you got to come out with a physical process, right? And also, because the thermocouple measurement was so difficult, we actually developed another way to do it, and this is using infrared microscope. But of course, the vapor itself doesn't emit much, So in this case, what we do is we put a very thin glass slide. That thin is important because it avoids the conduction in the vertical direction. And you measure the temperature distribution using IR imaging, and this is really puzzle, right? You see here is the lamp. Immediately you measure temperature after lamp is off. Take the lamp off, and this is when the lamp is on. So when lamp is on, you see this flat temperature region, and then also you see the temperature is lower when the lamp is on. When there's a light, your air is actually cooler, right? So this was very exciting. In fact, we had this data 2019. We spent the year by the end, we had those data, which is puzzled, and, but we couldn't come up with a real mechanism. Of course, we're familiar with hot electron, so could this be hot electron? But by that time, there are a lot of experiments from Gui Hua's group, not us. They put a polypyrrole, they put a carbon black, they put a titanium dioxide. They say, oh, they can get super evaporation rate. And they say, this can be the hot electron. And not from this particle. Could this, they were using polyvinyl alcohol, and say, okay, could this be the molecule itself? But we know this molecule do not absorb in the visible light. So basically we're stuck, right? We couldn't come up with a physical picture. And again, Gui Hua, they had they used this picture that people developed before. There are three kinds of water. One is bound to the water molecule, and then intermediate, and the outside is bulk. And they say the intermediate water has reduced latent heat. And they have some DSC, differential scanning calorimetry measurement, and we did this. And yeah, you could see some reduced latent heat, but you never really see a factor of 2 or even higher reduced latent heat. So then they have another experiment that really puzzled us. And this is, they put a black carbon paper, and they put a clear polyvinyl alcohol. And they say they still have a super thermal evaporation rate. And in this case, because I thought polyvinyl alcohol doesn't absorb, so clearly the light gets into black carbon, that's heat up, and that's a thermal process. I said, it's a thermal process. And we couldn't come up with our own picture. We say, okay, let's check their picture, because they say it's a thermal process. So we say, okay, let us electrically heat. Right? It's a thermal process. I don't need the light. I just need to heat up. And so 2020, we're doing this experiment, basically with the COVID, but it was difficult because we were not able to make their sample. So we make this electric heater. We have to embed it into the polyvinyl alcohol. And so I keep asking Yao Dong, I said, why don't you push closer to the surface, right? Because the solar is absorbed at surface. And, but see, in this case, we never get above 1.5, the thermodynamic limit, right? So we're stuck. And then in 2021, I was cut off. So, but I got time. I couldn't talk to anyone. I suddenly found I don't need to write the recommendation letters to anybody. So I suddenly have all the time. So I started reading. And this is the one thing I came over here. I say, your faculty actually really have very good, really has a lower, what I say, the lower administrative burdens. And I got more time, which is great. So I got time. I went to check literature. And then this is the sense my postdoc told me before, but I just didn't get into my mind. I didn't read literature. And then when I read it, I was saying, my gosh, there's so many papers reporting this super thermal evaporation. And they use different absorbers, and they use different polymers, And then they used long polymer, because I saw the polymer has something special, right? But they carbonize all kind of trees, vegetables, and there is a paper, is actually somebody I know, and he went to carbonize the cow manure, right? And I actually like that approach because you don't need a freeze-dry type of processing. And they all reporting different kind of outrageous value to me. Let's say some of this are reporting 7, some report 10, right? But say Gui Hua's group, they were getting like 5. So this is a really something there. It's more than just the say polyvinyl alcohol. That's what we knew. So in June 2021, I got a permission from the legal side that I could talk to the postdoc. I was really curious. And I asked him whether he had the progress. And he said no. He was trying to push those experiments, but couldn't get to about superthermal by electrical heating. So it's at this time I start to say, I think I know what's going on, because I did a lot of reading. I say, what's common of all these materials? And the only thing common to me is a large surface area. So I say, okay, is there anything that could happen at the surface? Could light actually be absorbed at the water-vapor interface? And I know one example, we all know this example, photoelectric effect, right? A photon can lock out electrons. So could similar process happen at the water-vapor interface? And there are 2 problems, of course. One is water does not absorb, right? And the other is the energy doesn't quite match. Because even I think about the cleavage process, the hydrogen bond energy is 10 times smaller than green light energy, right? But at that time, I was actually have done a lot of reading. And in fact, I was really happy. I was invited by editor of General Heat Transfer. He wrote me email. So after several emails, I started to say, okay, I'll do it. Because he asked me to write something for General Heat Transfer, and he probably knew I had time. I was actually at the beginning debating to write something on solid. I worked on that all my life. But I said, okay, I'm going to learn liquid anyway. So I spent 2 months. I read all what I could. I want to understand liquid. So I wrote a review on that. And that led me to appreciate better the hydrogen bond in water. And the water, people say the cluster water molecule form hydrogen bond network, or some people say that that's other clusters. But so the idea is, what if a photon cleave off many water molecules same time? And in that case, you don't need to break all the bonds. Then you can satisfy the energy, conservation, and you could have a superthermal. So that was the hypothesis. And again, water, I learned, people say is the most complicated liquid. And that's, really, in terms of the hydrogen bond, people don't agree. How large are these water hydrogen bond? And some people say it's 4 molecules to 8 molecules. Some people it's 200 to 300 molecules, right? So that there are big variations. But nobody denied their hydrogen bonds network there. So here's the physical picture I hypothesis, right? Because you still want to say, what would be the driving force? And the driving force is at the water-air interface, you get a dielectric constant, a factor of 2 difference in the visible frequency range. And the water-air, the liquid interface is only about 3 angstrom. You look at the molecular dynamics simulation, people about 3 to 5 angstrom, right? And now you have a polar, just an even single polar molecule. And you think about water itself, the dipole moment, based on that is about 0.5 angstrom. You think about that, you got 0.5 angstrom positive charge and negative charge, and then you got a gradient, a factor of 2 change over 3 angstrom. So basically, you got a 10% of the left force imbalance at the interface if the light comes at the angle. So that sort of gave me a hand-waving argument that I can convince myself maybe there is this process. And so I at the time I could Zoom my postdoc, and the poor guy, he'd never done any optical experiment, but we're lucky we had just say UV spectrometer in the lab. So I was asking, why don't you go to measure pure hydrogel? I always assume doesn't absorb. And now this time, you want to drop a little water into hydrogel. So there are a lot of interface. We don't want to flood the water, flood the pores. We need an interface. So he did this experiment. And in fact, even, so here, the black curve here is a polyvinyl alcohol, say PVA powder. And this is a few percent really within the experimental uncertainty because we measure using integral sphere. And the water itself doesn't absorb. But when he uses freeze dry, that's a part of the process. He starts to see absorption. And then when he dried, he add a few drops of water into hydrogel. He see very strong absorption. This is about 20% absorption. And so it depends on water content. If you got too much water, the absorption starts to drop. And not much water, there's no absorption. So that seems to be putting us on the right trajectory. So I was very excited. So we started to do evaporation from pure hydrogel. And this is a pure hydrogel, no absorber inside. And you can see they're very similar. This is a pure hydrogel. This is a hydrogel with a polyvinyl alcohol, PPY, polypyrrole. And there are 2 steps. The first step is when water covers the surface, you don't see a high evaporation rate. You need the water gets into the pore material. And in that case, you have a lot of surface, and you see the faster evaporation rate. And of course, the pure hydrogel doesn't absorb, completely absorb. But if you normalize it to the absorptance we measure, you got a superthermal way beyond other, even the polypyrrole with the polypyrrole. And this is another experiment. By then, we could make a similar sample as Guihua. We put a carbon paper, black carbon paper in the back. We put the polyvinyl, clear polyvinyl alcohol on top. And then you shine light from top or bottom. You see only when the light goes from top, it has this process. When light goes from bottom, it doesn't have this process. Right? So that's another sign. And again, in even purely polyvinyl alcohol, we saw the peak happens around the 500 nanometer, right? Green light. We still don't know why, but it happens. And it happens, in fact, that when the weakest light, it has the strongest effect. So this is sort of all, at least consistent with the idea that photon could actually cleave off water molecular clusters. And then we measure the vapor side, right? In this case, we have to heat up, because if we don't heat up, there's no rising plume. So we heat it up, and we compare to pure water, thermally heat up, versus the optical heat up. Again, you see much steeper temperature rise. You see a flat region in the vapor phase. And the physical interpretation is that now if you have cluster coming out of water, and they will break in water, in air, and that breaking absorb heat, And that absorption of heat also could saturate the vapor. And once the vapor gets saturation, you don't have further dissociation. And that's why you have flat temperature region. So the final, so in fact, you can say we actually could observe the fume coming out. And this one is, we went to the UV-based measure spectrum, right? So in this case, so we put our LED into the UV rays, and then we measure the vapor phase transmittance, and you actually could see some peak shifting there. And we don't know. We don't know what are those clusters. We don't know the size, but we say, okay, there are difference as we change the height. So those were the hydrogel experiment, and in fact, based on this understanding, we actually say why we had difficulties before to repeat the experiment. So basically, we think there's both internal process, external process. So when the hydrogel, the molecular cluster can come out of hydrogel, then you measure weight loss, much bigger weight loss. But if it recondenses inside the pore, you just generate heat. So in that case, you don't measure weight loss, superthermal, say evaporation rate. So that's an internal process and external. So you need to optimize the structure to get the maximum. So those are the experiment in pure. Actually, I turn off my phone. I was trying to look at time, so you can give me a warning. But what about a single interface, right? Can we measure a single interface? And because say hydrogel got too much random interface, right? So we want to say, can we measure single interface? And in this case, we should see angle dependence, wavelength I still don't understand, and polarization dependence. So I talked to Yao Dong. I said, okay, why don't you use a laser and let's try to do this. So he bought all these very cheap lasers. And the first time I got really excited. This is a student. I'm sharing all the failure or the trap we had, right? So I get really excited. You see here the TE and TM are different. And then we actually measure a very big difference. And this was just unbelievable. And but then a few months later, we found that when our light leak into the valence, they actually affect the reading. So we had to now go back. So this was actually now in 2000 say 2020, early 2020. Now we've been repeating the different experiment. So I'm going to talk about different experiment. So this is an experiment we're doing, trying to measure single interface absorptance. And in fact, I'm not giving you the scale because how to convert, we're still struggling. But I'm going to show the phenomena, right? So basically, the idea is laser heat the interface, they will have bending. And if I don't heat up water, and I think the cluster will recondense and generate heat. And when you generate heat at interface, you see temperature increase, you should see the bending because the refractive index change. So we do see that, right? You can see air-water interface, it depends on the power of laser. And you take a slope, you see this is the bending dependence on angle of polarization. So first you will see the angle. And this was actually, even though our balance experiment seems to have a problem, but we still see the peak. So you can see the peak now is about 45 degrees. And in fact, I told the postdoc, I said at the beginning, I said, you should aim at the 65, around 60, 55 degrees. And I'll explain why. But he actually found, through all this different experiments, we found the peak is not 55. And that was a puzzle that I think I have an answer. And this deflection, you don't see the scale because we're trying to convert into absorptance, and we're not really confident on that. But you see the phenomena here. Transverse electric field, that is, you have light coming in. Transverse electric is the electric field is parallel to the surface, and you don't see the effect. You see very small effect. And when transverse magnetic field, and this is when you have electric field component perpendicular to surface, you see the effect. So that's also you see here. It peaks at the grid. It peaks at the grid. That's what we saw in the evaporation, right? And we saw this peak at around 500. Here you see the peak around 500. I have no idea why this happened. And this is we measure surface temperature rise. And this is the infrared microscope. You can see this is the transverse electric and this transverse magnetic and the transverse magnetic TM field. You got a very sharp, very quick temperature rise, and which we interpret as the surface heating. And this is a thermal. This is still IR. You can see the surface temperature, TE and TM, mode difference. And peaks at 45, right? So that's consistent with the deflection experiment. And here is, we do thermocouple because we didn't trust the IR, you have to set the emittance. So in this case, the thermocouple is actually moving in, moving out, because you can't put the thermoconductor under light, it heats up. So when we turn off the light, we swing the thermocouple measure. And you can see the TM light still peaks at 45, and the IR camera is consistent. TE, you have a much smaller effect. And here is the temperature region. And you can see this is what we measured before. That's 2019 polyvinyl alcohol, PPY. Here is a pure water surface. You heat up the water, you shine the light, you see TE light doesn't have any effect, and TM light has a flat temperature region, just as we saw for the polyvinyl alcohol surface evaporation, right? So this was actually a result in 2021, and we were using LED. But those experiments, this is a laser. So again, all those we saw the flat temperature region. This is a recent spectroscopy experiment. So we put the water, pure water, we heat it up at 55 degrees in this case. And this is inside the UV vase, and we shine the laser at 45 degrees. And you can see between light on and light off, say this is black is light on, and red is light off. You see a huge difference, right? So all this seems to be consistent with the idea that the what we call this a photomolecular evaporation idea. And so why we're excited? Because you think about Earth is covered with 70% with water. You have clouds. You have ocean air interface with all forms of droplets. You have soil trapped with water. And you have all the aerosols. So this could have a big impact, we think, on how you model global warming, because the greenhouse effect of water is actually a few times higher than CO2 in the atmosphere. And so, in fact, this is when I was walking with my wife, had nobody to talk to, and at the beginning, she didn't quite believe me, and later on when she said, oh, the weatherman say when the sun burned the cloud. I said, we can do an experiment like that. So this is a cloud chamber, right? We generate the droplets of water, and then you measure the difference between with and without cloud under different LED. And you see, again, the green light, it peaks the temperature rise. And in this case, a much higher temperature rise because I got a lot of interface. So let me just briefly mention a model, and I said I probably don't have time to talk about thermal, and after this I'll stop. So there are only 2 slides here. I was puzzled. I couldn't explain wavelengths. I still cannot explain wavelengths. I think maybe relate to how many bonds, how many clusters were cleaving. But I was puzzled by this 45 degree. Because at the beginning, I was anticipating 55. I say it's a cosine theta squared sine theta based on simple number of photon flux relation. So here is what I say quadrupole is a dipole expansion of quadrupole. You have a dipole at the interface. And if the 2 point that the field is different, you expand, you have a quadrupole term. And then here's a very hand-waving going to the Fermi-Golden rule to say what's the scatter matrix. I say it's hand-waving because you need the wave function. I don't know the wave function. Okay. So, but you do the quadrupole, you actually say it depends on the dipole orientation, right? And turns out that it's not just a cosine theta squared sine theta, it's theta minus alpha, and the alpha is the dipole orientation. And this alpha was actually measured by Chen at Berkeley, and he was doing some frequencies nonlinear spectroscopy. And so his paper said the water actually has a preferential orientation at the interface. So at least we could adjust this alpha to sort of match the interface, say the fact that we see a 45 degree peak there. But beyond that, very much hand-waving. So I'm hoping to collaborate with more people, and in fact, like I say, we couldn't publish it because people don't believe, so the more people work on it, the better, right? So I'm going to stop on this thermal evaporation, and I just summarize. I think there seems to be, this is really a puzzle, and we think we get the right, hook or on right track to answer this puzzle, because it seems that the experimental evidence in hydrogel as well as in pure water air interface can be all consistent. So with that, let me finish here, and really I want to thank my students. They are very persistent and postdocs, and I'm very grateful to the entire scientific community for the support. And like I say, I'm the luckiest among unlucky people, and actually I had the luxury to do research during a year of very stressful year. Thank you very much. I hope we'll have a little bit of time for Q&A.
Okay, thank you very much, Gong, for a very thought-provoking lecture here with simple experiments challenging our thinking. So I'll go ahead and ask for questions from the audience. Do you believe it?
Yes. You don't need to say whether you believe or not. Just to say, it's better just not believe it. What's the shoot down the idea? Yes. Yes.
So if you have a question, what we're going to do is run microphones to you here. We have a question here in the front. And we'll open here with a question in the front.
Yeah, thanks for the talk. So, I heard this after you were first, all the charges you dropped. We were all talking as the alums, and we were hoping, I would say for myself, to have a nice celebratory time, but you started talking about the photomolecular effect for around 20 minutes. So I heard about it then without slides.
Right.
So now that I see the slides, I understand it a lot better. And I was wondering, particularly, can you model what's happening without worrying about the clusters, but just as a surface loss in addition to, normally you have the bulk loss of water, which is very small. But I think I understood part of this is that the water at the interface can absorb more than one would expect based on the bulk loss. Is that the right way to think about it, or do you still need the concept of clusters cleaving off to explain the magnitude of the effect?
So we need the concept of cluster to explain why you can have a loss of mass, the weight on mass beyond the thermal evaporation. So basically we're evaporating more molecules than what we typically think about thermal evaporation. And on that, the cluster picture seems to be less straight, right? And beyond that, it's all, I would say I'm sort of confident, my confidence is built not only because of the experiment, but also I say, okay, I can at least hand-wavingly explain why the peak is around 45 degrees and not 55 degrees. Yeah.
Okay, a question right here.
Would you expect similar effects with some other material that's not water but also has hydrogen bonds?
Actually, yes, absolutely. This is what I think. In fact, I was thinking that this should happen in other material. And among all the people, there was one person that was not surprised, and I was at Berkeley last year, and I was talking to Eli Yavlovich. And he told me something that surprised me, because he said, all surface, so the surface absorption is an intrinsic property. And he told me a number. He said that gallium arsenide has 10 to the minus 4. And he said the book never mentioned this, and nobody understood. So I actually think this is all related. But I was actually during the past, I looked into people doing the long thermal ablation. I was thinking whether that's related, right? A lot of people doing laser ablation on surface or laser desorption. I think there are many mechanisms, but this quadruple expansion of dipole field mechanism, I haven't seen people talk about that. So I think this could be common in other material. In fact, he even told me on silicon surface, 10 to the minus 7. I was surprised that he knew these numbers.
Okay, other questions here?
Rick.
You have a hand raised.
Very interesting talk. For your hydrogel experiments, have you considered looking at well-structured materials? I'm thinking specifically of zeolites as a porous material with well-defined pores that might give you an additional handle to go after in the physics.
Yeah, that's an excellent question. In fact, I think Julia, she does a lot of 3D printing of regular structures. So there are people working on regular structure. It turns out for those transport, you need a combination of macropoles, which is we don't know exactly what's the optimum, and most of the time seems you need a tens of micron to even 100 micron, so that vapor transport is easier. But you also need those nanopores so that the water sidewall of this pore can be flooded with water. So that hydrophilicity, the other part of making this material is the hydrophilicity, hydrophobicity control of the surface. And it's something that we're still learning.
People have been working for years on how to engineer the chemical and physical structure of zeolites. They have pores down in the nanometer range,
right,
which gives you access to the fine part.
Right.
And they're commonly configured in ways, in catalysts, to give the macropores as well. So you might have access to a class of materials that would give you additional handles to go after what's going on with the porous material.
Yes, yes, I completely agree. So there are so many things we really don't understand, and the optimization is wide open. In a way, we're also optimizing under dark. We don't know what we'll see physics mechanism, right? So, yeah.
My question was, how well do we understand photon cluster interactions? Because I see there was a parallel drawn with photoelectric effect. So do we have similar concepts like a work function, like there's a certain frequency below which we won't see this kind of an effect? So do those kinds of phenomena carry over?
Yeah, that's an excellent question. And this is where you see the complexity. We don't understand. So basically, you see, we don't understand. I keep saying that the wavelength dependence, I have no understanding, because why happen at the region where water is least absorbing, right? And my picture is more like, okay, I do a lot of in the past electron. When light absorb electron, it lifts from the valence band to conduction band. And that happens only in the conduction band that has empty states. So it happens at the interface, to me, is more like there is a vacancy state nearby, right? So you can lift the cluster. But in water, bulk water, maybe there's no empty state. Maybe that's a reason. It's just a thought. But of course, if this process happens, then is a cleave and van der Waals bond, the hydrogen bond and network bonded together. And but the van der Waals bond may be cleave, but how you could cleave in that case over 100 bonds with one photon? I couldn't wrap my head around it, right? And so it is a lot of things that we really don't understand.
Thank you.
Thank you for the great talk. I was intrigued by the distinction between TM and T light. So it looks very similar to the Brewster, the Fresnel equation, Fresnel coefficients. Have you considered the optical properties within this process?
Yeah, we went to, of course, you can take water and you calculate the Fresnel coefficient reflectance. Of course, you have peaks, but see the change in that is very small. Okay, so it doesn't explain the experiment.
Okay, thanks.
Yeah.
So we'll take one more question here for Professor Chen. I'm sure everyone is going to be wondering about this on their way out the door and home tonight, and you can email him after the lecture.
And you can do the experiment yourself. It's simple.
Yeah, send him your results.
You could make a lot of mistakes, guys. We did, but it's simple enough.
So right here. Yep, go ahead.
Yeah, so I guess looking at this, I wonder if a parallel can be drawn to something like the Jellium model and explaining like particulate clustering and atom by atom addition, right? Like you start with a gold atom, you add multiple gold atoms, they form planar sheets into like 25 atoms, and then they form clusters of different magnitude and size. In those sort of models, right, the addition of the single atom, or in your case, water, destabilize the cluster and cause a significant reconfiguration of the normal modes. I wonder if there's a similar atom by atom approach to the structure of the cluster that might elucidate green light, because that could be the associated frequency for destabilizing that mode and transitioning to a new set of normal modes for a new cluster, or smaller set of clusters.
Yeah, those are all good hypotheses. In fact, water vapor interface is never flat. It's you go to say there are a lot of people study using synchrotron source to say, okay, the roughness is a few angstroms. So there are thermal capillary force. In fact, I had a meeting with John Pendry, and his first reaction was this could be an instability, right? So I'm not quite convinced it's an instability, but I think they're rolling mode, right? So that's why the TE mode is not completely zero clean. And because when you have empty space for the molecule to go, TE mode can still get, because the surface roughness is not completely pure TE modes. So we have those sort of hypotheses that could explain the observation, but no model, no quantitative model.
Okay, so let's thank Gong Chen here.
Thank you.